Hey there, welcome back. In this video, we're going to talk about the queue data structure. So let's go ahead and begin. So queues are a first in, first out data structure, also known as a FIFO data structure. Okay, this means that the first value that we place into it is going to be the first value that comes out. These are used to model things like, for example, real world analogy would be a line at a grocery store, right? The first person that is in the line, or that enters the line, is going to be the first person that comes out. So similarly with a queue data structure, the first item that we store in the queue is always going to be the first item that comes out. So in this video, we'll examine an array-based queue, which is also known as a static queue. All right, so let's define 5 basic operations for our queue. We will have isFull, which is used to determine if there's room to put another value into our queue. isEmpty, which we'll use to determine if the queue is currently empty. InQueue, which is the operation for adding new values to the end of our queue. And DQ, which is used for removing values from the front of our queue. And then we'll have a peek operation, which we'll use to return a copy of the first value in the queue. Okay, so here's a quick example of what we're talking about, right? So let's say that we have a queue and the front of the queue is going to be towards the left of the slide and the back of the queue is towards the right. So what's going to happen is that all of the values that are added are going to be added towards the right, right? And all the values that we're going to remove are going to be removed from towards the left. Okay, so let's say that we wanted to perform an in-queue operation. Assuming there's room, we'd go ahead and place that into our empty queue. So here we've got 8. Right now, if we were going to do another in-queue operation, assuming there's room, the value would be placed behind 8. Right? So now we have 8 and 6. Front is 8, back of the queue is 6. So let's say that we're going to in-queue another value, assuming there's room. Go ahead and place that value behind the 6. Okay, and if we do one last in-queue operation, assuming there's room, place that 5 behind the 7. So all of the values being added are being added to the right end of the array. Okay, now let's say that we wanted to remove values from the queue. If we wanted to do that, then we'd be performing a DQ operation, and all the values that are being removed will be removed from the front or from the left end of the array. So we do a DQ, assuming there's something in the array or inside the queue, go ahead and remove that value. If there's something inside the queue, go ahead and remove that value. If we want to do a third DQ operation, assuming there's a value in the queue, go ahead and DQ. And then assuming there's something in the queue, go ahead and do another DQ operation. Okay, so we're back where we started from with an empty queue. All right, so let's examine how this could play out in memory. Here we have a memory map representing an array of 4 elements, which we'll call A. And in addition to that array, we're going to need to have 2 variables, one named front, one named back, and both of these variables we will initialize to 0. Right? So the front variable is going to contain the index of the first value, or of the element that contains the first value of our queue. Okay, and back is going to contain the index of the element where we will write new values, or where we will add new values to our queue. Okay, going to be slightly different than what we're defining front as, because back is not going to have an index of an actual value in our queue. It's going to have the index of the element that contains, or of the element where we're going to write our next value. Okay, so it's a little bit different. So also notice that we haven't added any values to the queue yet, so nothing's showing up on our array here. So it's going to represent, or when front and back are both the same value, that's going to represent that our queue is empty, right? So we'll initialize, we have both of them initialized to 0. So in this case, our queue is empty. That isn't to say that the array is empty, right? Remember, there's no such thing as an empty memory location. It just means that theoretically there's nothing in our queue yet. Okay. Anyway, so front and back the same, empty queue. array doesn't have anything showing here because we haven't had anything yet. Now let's say that we want to enqueue a value. Okay, so what's going to have to happen is, first thing is, check to see if the queue is not full. Okay, and I'll explain that operation here in just a second. But queue is not full, so go ahead and write to the back, in this case 8, and then increment back. Okay, so 8 is now the front, and our front variable reflects that by having the index of that value, of that element that contains that value, and back has been incremented to 1. That's going to be where our next value goes to. Okay, so let's say we do another enqueue operation. Okay, first we write, or we check to make sure that there's room, there was here, and then we write the value to the back, and then we increment back. Okay, let's say we want to do another enqueue operation. We're going to check to make sure that the queue is not full, and then if it's not, we will write to the back, and then increment back. Okay, so let's say a couple of examples of dequeuing now. So let's say that we wanted to remove 8 from the front of our queue, right? And right now our queue currently contains 8, 6, and 7. Front of the queue is at element 0. Back of the queue is at element 2. But remember, the back variable represents where we would add the next value to, right? So it's not 2, it's 3, because back contains the index of where the next value would go. Okay, anyway, so we're going to do a dequeue. So all we have to do to remove 8 from our queue is to increment front. Okay, so now front is, or the value that's at the front of our queue is now 6, and it's in element 1, so front contains 1. So let's say that we wanted to remove 6 now. Okay, then all we have to do is increment front again. Let us assume that we wanted to do some more enqueuing. Let's say that we wanted to add another value. Okay, now right now our queue only has one value in it, right? Because we did a couple of dequeue operations, and the front of the queue is in element 2, and the front value is 7. Of course, the last value is also 7 because 7 is the only value in the queue. But the back, where we're going to write to, is at element 3, okay, which is fine. So let's say that we want to enqueue our next value, say 5. Okay, so the enqueue operation is a 3-step process where we first check to see if there's enough room, right, which there was because we had the extra space there. But then we would also have to, we check if there's enough room, then we write the value. Next, we would have to increment the back variable, right? Now, you may notice there's a problem here. If we increment back, what's back going to contain? It's going to contain 4. 4 is not a valid memory location, or for us anyway, right? It's not part of our array because the only valid indices are 0, 1, 2, and 3. So what does that mean? Well, it means that we can't leave it at 4. We're going to have to reset it. We're going to have to do something with it. So what we'll do is we'll wrap it around back to the front of the array. We'll reset it to 0. Okay, so why would we do that, or why does that work? Well, first of all, we have to make sure that we don't go out of bounds with our array. But we dequeued 8 and 6, right? The front of our queue is an element 2, which leaves elements 0, 1 available to be reused, right? So now, after wrapping around the back variable, right, resetting it back to 0, the next place that I'm going to write a value is going to be in the first element. Okay, now the front of my queue is still going to be at element 2. That's what the front variable indicates, right? But right now, my queue contains 7 and 5, and the next value that I add is going to be at the end of 5, but we've wrapped it around. We're storing it differently than we're thinking about it, or how it's being, or how our queue appears in the abstract. In the concrete, it's actually being stored in this kind of a wraparound fashion. So now if I wanted to do another enqueue operation, what would I do? I'd first assign the value to the back, in this case 3, overwriting the 8, and then I would increment back to 1. Okay? Now, let's say that I wanted to do one more enqueue operation. Could I do it? Answer is no, right? Because look where the back is, right? If I did another enqueue operation, I would have to write to the back, which would store the value that I wanted to add in element 1. That's not a problem, right? Which would bring up my total size of my queue to 4 elements. The problem comes when I increment the back again, right? If after that in Q I increment back, what's the value going to be inside the back? 2, right? But front's also 2. So if that's the case, remember at the very beginning of this example, we talked about how a Q is considered empty if both front and back are the same. So I can't do that. We can't have that. So what that means is that our Q is going to be considered full when the back variable is 1 behind the front, or the back of the Q is 1 element behind the front, right? So in this case, front's 2, back's 1. All right, so let's take a closer look at this wraparound logic, right? Now, both front and back will eventually have to be reset back to 0, right? Both the InQ and the DQ operation cause the front and back variables to be incremented. So eventually, just like back will move past the end of the array, front would too. So they're both going to have to be able to be reset back to 0. That's what we're talking about with this wraparound logic. Okay, so we've got 2 options to do this. One is to utilize modulus. Okay, and so by finding the remainder of the sum of the variable, in this example front, for example, plus 1, if we divide that by the length of the array, we're going to get ourselves back to 0. Okay, I'll leave that as an exercise for you to work out the math to see why that's true, but it's true. Okay, if that's too confusing, or if that makes you freak out, then an option is to just merely use an if statement and an assignment statement. So if we get to the point where front is equal to the length of A, remember what the length of A will be, right? If A is 4 elements long, that means that the valid subscripts are 0, 1, 2, and 3. If front currently contains 3 and we do another NQ operation, front's going to become 4, which is the length of the array. There's 4 elements, right? So that's why this is going to work. So anyway, if the front is set to the length of A, then all we have to do is reset front to 0. That's it. That's all there is to it. Use whichever one you're most comfortable with. All right, so let's go ahead and examine the algorithms in more detail. So the algorithms for making this happen, there was is full, is empty, NQ, DQ, and peak. These are all constant time algorithms, which is to say that all the steps in each of the algorithms, they are fixed in size. There's a fixed number of them. They're not going to vary. The number of steps that you have to, or the number of operations you have to perform, is not going to depend upon how many elements are in the array or how many values are currently stored inside of the queue. This makes each of these algorithms a constant time operation, which is big O of 1. Okay, so let's bang these out and look at them really quick. Let's get through these. So first one we'll look at is full. Okay, we already talked about how if the back is 1 position less than the front, then our queue is full, right? And so we're going to use modulus in this example to support the wraparound logic, because it is possible. I mean, if you sit down with pen and paper and trace through this a couple times, you'll see that the back and the front aren't always going to be in the order that you would normally think of front and back being, right? So we have to support the wraparound logic. That's what modulus is doing. So if the sum of back in 1 divided by, or modulus, length of A, I should say, equals the front, then we'll go ahead and return true. False otherwise. Okay, and this implies that, again, just as a reminder, that we're going to have 1 element in our array that's not storing anything for our queue. It's just a side effect, just something that we have to live with. Okay, so what about is empty? Well, we talked about this in the example. If the front equals the back, no matter what that is, 0, 0, 1, 1, 2, 2, etc., then we return true. That implies that the queue is empty. Otherwise, we return false. Okay, what about in queue? This is the operation for adding a value to the end of the queue. So first thing we're going to do is check to see if the queue is full or not. If it's not full, then we have room to add another value. So what will we do? We'll set the A of back to the value to be in queued, where A is the array we're using to store the values for the queue. Okay. Then what we have to do is we have to increment back. Okay. And so in this implementation of the algorithm, using the modulus approach. So set back to the sum of back plus 1 modulus length of the array A. Okay, that's all there is to it. What about DQ? If we're going to remove a value from the queue, from the front of the queue, then first thing we have to do is make sure that the queue is not empty, because you can't remove a value from an empty queue. And then if it is, let's go ahead and increment front. Okay, and in this implementation of the algorithm, we'll use that combination of if and assignment statement to implement the wraparound logic. So we'll set front to front plus 1, we'll increment front. And then if front equals the length of the array A, then we'll go ahead and reset front back to 0. So if we go 1 position past the end of the array, let's reset front to 0. Okay, and that's all there is to that. And then finally, one last really quick algorithm, peek, and peek is going to be the algorithm that allows us to get a value or a copy of the first value in the queue out of the data structure for further processing. Right. So if the queue is not empty, then go ahead and return a copy of the front value, return A up front. Okay, so let's go ahead and summarize. So in this video, we saw that queues are a first in, first out data structure, and this implies, as we saw with this implementation and the example, that values are going to go in one end of the array and come out in the opposite end. Okay, we define 5 basic operations: is full, is empty, enqueue, dequeue, and peek. And we saw or took a closer look around this wraparound logic and examined 2 ways to implement it. One method was using modulus, and the other was using a combination of an if statement and an assignment statement. Great, so that's everything. If you found this video useful, please consider hitting that thumbs up button, maybe hitting that subscribe button. Really helps out the channel, lets me know that this was useful for you. And if you thought that the video sucked, well, there's that thumbs down button available to you as well, right? As usual, if you are a student of mine and have further questions, please feel free to shoot me an email or stop by my office hours. Thanks for watching, and we'll catch you next time.